In this video, we're going to continue talking about the central limit theorem, which means as we sample more and more individuals, it becomes closer and closer to a normal bell-shaped distribution. But in this case, we want to look at proportions. Proportions are very similar to probabilities. We are just given the actual frequency and the total sample size. We aren't given that actual probability instead. So a sample proportion, p hat, is equal to the x divided by n. X is just looking at like our frequency divided by our total value. So a lowercase p in this particular case is going to be our population proportion. So we're looking at population proportion. And whenever we do, we have to estimate that using our best estimate, which would be p hat. P hat is our sample proportion. Because maybe we haven't proved that yet that it is a single value or a probability, so we actually have to look at the proportions. These are whenever you're doing your own sampling or anything of that nature, we want to look at these items. The mean for our proportions, so for p hat, is going to be our p, our population proportion. That's what we're looking at. That's going to be our mean. Now our standard deviation is going to be our proportion times 1 minus p divided by n. And we have to take the square root of that. So it's our proportion times the proportion of those that do not do this type of thing divided by n, and we always have to take the square root because we want the standard deviation. Let's look at an example. The National Center for Educational Statistics reports that 75% of freshmen entering public high schools in the United States in 2007 graduated with their class in 2011. So 75% of incoming freshmen graduated with their class 4 years later. So where we want to find the mean, we know the proportion of students that actually graduated, and that was 75% or 0.75. We know that we looked at a sample of 135 freshmen, and so we want to know the proportion of these that will actually graduate with their classmates. Well, our mean is very straightforward. It's just going to be the proportion that do actually graduate, which is 75% or 0.75. Now when we look for the standard deviation, so we want the standard deviation, it's going to be the p times the 1 minus p divided by n, and we're going to take the square root of that. So for our standard deviation, our p was 0.75 times 1 minus 0.75, and we had a sample of 135 freshmen. Well, 1 minus 0.75 is going to be 0.25, so we're going to multiply that by 0.75, then divide by 135, and the last thing that we have to do is take the square root. So 0.75 times 0.25 is going to give me a 0.1875. We're going to divide that by 135 and take the square root. Now when I divide, I'm going to get 0.00138888889. And I want to take the square root of that. You'll notice that I wrote down everything that could have been in my calculator. I do not want to round until the very end. So please don't round here. I want to wait till the very end to round. When I take the square root of that, that's going to be a 0.03727, which we can look at as being 0.037. This would be the standard deviation. So 68% of our data falls within one standard deviation of our mean. Now the hardest part about this is remembering what our values are. Let's look at the central limit theorem. Let p hat be the sample proportion for the sample size n. If n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10, then we can assume that the mean is our proportion and the standard deviation is that what we just calculated. What we're saying is we have a large enough sample. If we do not have a large enough sample for these to be greater than or equal to 10, then we don't know for sure that it's normally distributed. If it's not normally distributed, I can't use any of these calculations that we've been using up to this point. So let's look at example 2. High blood pressure has been identified as a risk factor for heart attacks and strokes. The National Health and Nutrition Examination Survey reported that the proportion of U.S. adults with high blood pressure is 0.3. So that's saying that our P is going to be 0.3. A sample of 38 U.S. adults is chosen. So N is going to be 38. Is it appropriate to use the normal approximation to find the probability? And we want to explain. So in order for it to be appropriate, we have to look at N times P. Is it greater than or equal to 10? And we have to look at N times 1 minus P to see if it's greater than or equal to 10. If either one of these are not greater than or equal to 10, again, we don't have a large enough sample. So let's look at if we have 38 times our 0.3. That is the N times the P. Well, 38 times 0.3 is going to be 11.4. Is that greater than or equal to 10? Yes. So this one checks out. Now let's make sure that the other one checks out. N times 1 minus P is going to be 38 times a 1 minus 0.3. 1 minus 0.3 is going to be 0.7. Well, 0.7 times 38 is 26.6. So since both of these are greater than or equal to 10, it is appropriate to approximate the probability with the normal approximation. Since it is appropriate, we want to find the probability that more than 40% of people in the sample will have high blood pressure. So we have 40% here. Well, if we look at our number line and our curve, the mean is 30%, 0.3. I want to look at 0.4 and greater. So I want to see if this one is. When we use this, our Z is going to be our P hat minus our mean divided by our standard deviation of P hat. Well, again, P hat, that's just looking for what value that we're comparing to. So our value that we're comparing to is 40%, 0.4, minus our estimated mean, or our estimated probability of 0.3, the proportion that are actually have high blood pressure. Then recall that sigma sub p hat, and I might go over to the side and say that sigma p hat is going to be our p times 1 minus p divided by n, and we take the square root. So p is 0.3 times 1 minus 0.3 divided by 38, and we need to take the square root of this. Doing these calculations, we should come up with approximately 0.0743. Notice I kept 4 decimal places. I want to keep as many as possible. That is going to be the standard deviation that we use to calculate our z-score. So 0.4 minus 0.3 is going to be a 0.1 divided by 0.0743, which is going to give me 135. Or, I'm sorry, 1.35. Well, 1.35 is strictly my z-score. So I'm going to have to look that z-score up on my table. So go ahead and look at it, see if you can figure it out. So you might want to pause the video at this point. But wherever we look up 1.35 on the table, recall that it gives me to the left. And it's going to give me a 0.9115. But I want to the right. So I have to do the probability that p hat is greater than 0.4 is equal to the probability that z is greater than 1.35. I'm going to take 1 minus that 0.9115, and when I do 1 minus that, it's going to be 0.0885. So the probability that more than 40% of people in the sample will have high blood pressure is 0.0885. On these, we're really looking at the fact that we're not given actual values. We're given proportions. We're given probabilities that we want to compare to. Anytime that we're given these proportions, I need to find the standard deviation for proportions, which is going to be that p times 1 minus p divided by our sample size. Remember to take the square root of it. We can't calculate these just value minus the mean divided by standard deviation, because our standard deviation, we don't actually have a standard deviation. We actually have to calculate that because it is proportions. Now I'd like for you to try some of these and then let me know if you have questions so that we can discuss them.